Okay, one moment, guys. I'm gonna make sure I'm sharing screen here. There we go. Okay. All right. So, welcome back from the nice long weekend. So today we're going to talk a little bit about some alternative coordinate systems, and maybe get a little bit into section 3.1 as well, which deals with graphs and parametric functions. And we'll continue that on Thursday. So next week we have an exam, our first of the 3 hourly exams throughout the semester. And what I want students to be able to do is have their homeworks graded before their exams, or at least have had the chance to turn in the homework for the material that'll appear on the exam. So this week will mark sort of the end of the material for the first exam, which will take place next week. And I know SAS will have a review session, and I'll also have a review session. I'm not sure if I'll do just a Zoom review session or just or do it in person, but either way, I'll record it and people can look at it online if they want to. I'll make an announcement on timing for that, maybe Thursday and Tuesday. All right, so let's just review a little bit about what we talked about last time, just so we know how we're continuing. So last time, we talked about quadrics. And there were a couple of examples that we looked at. One was just like this notion of an ellipsoid, which is like an egg shape. And its form was something, I mean, and again, I don't need you to remember the names of things, but that's something I'm happy with you just looking up in the book. So if you have some kind of equation like this would be an ellipsoid centered at the origin, where A, B, and C, were all, actually 4 of these say, they're all positive numbers, positive real numbers. And we also looked at a hyperboloid, which was just, had kind of a shape like this. Sort of like a, I don't know, kind of funnel or something. And here it's the same sort of equation, but one of the coordinates, in this case I think C, is going to be less than 0. So all of them look the same. But we didn't get a lot. I think I kind of tried to sketch something very quickly at the end, but it's pretty rushed. So I just wanted to mention the main quadrics that we want to know about in this class are going to be sort of what are known as paraboloids. So they'll have equations where this z² terms is really just is not there, and rather it's replaced with a linear term z. So you can have some kind of like equation like z equals x² plus y², or z equals x². Well, let's say I'll give it different, minus x² minus y². And then I'll just do one more, say z equals x² minus y². So you really are just playing with the signs here, and of course you can scale these. They don't have to be plus or minus 1. You can scale the coefficients for x and y how you wish. You can center it over different points, but okay. These are all paraboloids. And why these are important for us is because what we want and what we're going to get into, and I'll just parenthetically put it here, are to look at graphs of functions, say of 2 variables, okay? So we're going to be looking at graphs of functions, and it's just like in one variable calculus at z, like y equals f of x, and you try to understand that behavior of that function. So if you recall in one variable calc, and we'll go over this again in a few weeks, in one variable calc, you know that your first naive approximation, you want to call it that, of a function is you take the value of the function at the point you're interested in. That just gives you a constant kind of approximation. But then you use calculus and you find a derivative and you get a linear approximation, right? And when you then try to extremize functions in one variable, you find critical points and then you do a second derivative test to see whether or not the function looks like, you know, this or some kind of, you know, inflection point, right? So everyone remembers this stuff? So this is from Calc 1. And basically, the reason that the two pictures that you have look like this and this are because the two kind of quadrics, or quadratic functions, in one variable look like x squared, y equals x squared, or y equals minus x squared, up to some scaling, you know, positive scaling. So I'm trying to emphasize why we learn quadrics in this class is because we want to do a similar type of thing. We will do a similar type of thing a little bit later on, where we study sort of the second degree part of a two variable function, and we'll get these kind of three prototypes. Okay, they'll tell us about the behavior of that function near a point in two dimensions. And here you get kind of a picture, you know, like this, just looks like a parabola, but you kind of have this rounded top. So that looks like sort of a, you know, a relative min. You can get a relative max, which I'm just going to sketch it here like this. And again, we'll talk about this more. And then this third one really illustrates the behavior of higher dimensions, or a novelty in higher dimensions, which you don't see in one-dimensional calculus, which is you don't always have a function that has a relative min or a relative max. Sometimes you have a function that, depending on the direction you go, it's a relative min and a relative max. So this, as I said last time, you get something like a saddle, and it illustrates kind of right at this particular point, illustrates this kind of behavior. So if you're going in this direction, you have a relative max. In this direction, you have a relative min, and that's all concentrated at that particular point. So these this is why we study quadrics in Calc 3, is we're sort of aiming for these types of models later on. Now, and you might ask, well, why are we studying these types of quadrics as well? Well, those types of quadrics tell us about actually the behavior of a function of 3 variables instead of a function of 2 variables. And of course, you can go into higher dimensions as well. Okay, so I wanted to kind of post-motivate some of the ideas there before moving on to polar coordinates. So let's do that now. So let's recall polar coordinates. This is just a review. I know many of you have seen these, and if you haven't, don't worry. And really, this is just a way, a different coordinate system rather than Cartesian coordinate system. This is a way of writing equations of shapes in the plane or points in the plane that utilizes the symmetry of sort of the rotational symmetry of the plane. So really what we want to look at is, let's say we have a point in the plane. Well, we know that in Cartesian coordinates, we know that what we do with this point is we just drop it to the x-axis, and here, if we want to measure this and maybe drop it to the y-axis too. And if we want to measure these, find the x and y, of course, we get the x length here and the y length here. This will give us the point xy. Okay, great. We all know that, hopefully. And now we want to do kind of a different system where we're going to, instead of measuring sort of the vertical and horizontal lengths here, we're going to measure just the distance to the origin. And so this will give us the coordinate r, it's the radial coordinate, that's that distance. And we'll also include a new variable, which is the angle made with the positive x-axis. We'll call that theta. And so we're going to call the exact same point in the plane r theta. Now, a couple of things to note about this coordinate system is that unlike the case where we have the coordinates x, y, where we don't have any bounds on x and y, I mean, x and y can be any real numbers we want. For the polar coordinates, we do have bounds. So we do want to restrict which numbers we put in for polar coordinates. In particular, we want r to be non-negative. And I want theta to be between 0 and 2 pi. And there's sometimes you'll see, I don't remember in the book or not, this might be a strict inequality. I'll just let it be either one right now, but maybe you can put strict if you want. Now, even if you did have a strict inequality, there is some ambiguity with polar coordinates, unlike the case of Cartesian coordinates. Cartesian coordinates, you give me two numbers, I give you a single point in the plane. And if you give me two different numbers, or one of them is different, I'll get a different point. That's not the case with polar coordinates. With polar coordinates, if r is 0, of course, theta can be anything. I'm describing the origin, right? And if I let, theta be 2 pi and 0, well, then I'm describing points on this positive x-axis in two different ways. And again, sometimes they won't allow the 2 pi case. Okay, so this gives us a picture of what these coordinates are, but if we want to really work with them, we should have some formulas. And the formulas we get, basically you want both formulas. You'd like to be able to convert from xy coordinates, Cartesian coordinates, to polar and vice versa. So going from, if I have a set of polar coordinates, it's quite easy to write down the xy coordinates, the Cartesian coordinates. This is just some basic trig. You're going to take x is r times cosine of theta, and y is r sine theta. Just looking at the triangles that are staring us in the face. On the other hand, if we want to go, let's say we have our Cartesian set up and we'd like to find r and theta. For that, we need to, well, r, we have a distance formula in the plane, our Pythagorean theorem, if you will. And r we know is going to equal the square root of x squared plus y squared times dx squared plus y squared. We can use a little basic trig to realize that arctan of theta is going to equal y over x. That formula for arctan of theta, you have to be a little bit careful with, choose the right branch for the inverse function of theta. So you want theta to be in this range here. Okay. So this is polar coordinates. Hopefully many of you have seen this before. I doubt many of you have worked extensively with it, but it's something I think comes up in high school courses. So, and if not, then this is all there is to it, really. But so it may lead you to ask the question, why do we care about polar coordinates? Well, what's wrong with Cartesian coordinates? Nothing's wrong with Cartesian coordinates, they're fine. But there are some advantages to being able to change your coordinate system, okay? And these advantages, there are some situations that we'll get into, I think, when we talk about integration, for example, where I don't know of any possible way of solving certain problems without translating them into, say, polar coordinates. So there may be a way, but I've never read them, and this tool really does help you with some very difficult problems otherwise. So what is the advantage? The biggest advantage is these coordinate systems are best used to reduce the number of variables and or complexity in the presence of symmetry. And then the symmetry often talked about with polar coordinates be rotational symmetry, not the only one. So let me give you a very simple example of that. So example. Okay, so what's the equation? This is kind of ridiculous, but okay, equation for a circle of radius 5. Well, I'll say 3. Okay, so in Cartesian case, say centered at the origin. Of course, we get x squared plus y squared equals 9. And the polar coordinate case, the equation for polar coordinates is just r equals 3. So I want to say, I mean, it's really naive and kind of simple, but this equation is much more complicated than this equation. You have, of course, 2 variables in this equation, but moreover, you have quadratic terms, you have squares in them. And okay, that adds to complexity, it certainly does. Whereas this is a single variable, you're just setting it equal to a constant. It's much simpler, and you can use these types of things when you're doing calculus or integrating to simplify your problem. So there's not much of a jump at all from a polar coordinate, from a 2-dimensional alternative system of polar coordinates to the 3-dimensional system of cylindrical coordinates. It's a very basic kind of generalization. So let's talk about that. So all you do with cylindrical coordinates, this is a 3-dimensional system. So let me draw a 3-dimensional grid coordinates. This is our usual x, y, z coordinates, and I'm going to for later use copy that. So now if I have a point out here, right? Well, we know how to get the x, y, and z. I'll label these axes, x, y, and z. We just drop them to project them, if you will, to the various axes and find the length. Or if you want, make a big box. However, if we want to find cylindrical coordinates, well, let's give our cylindrical coordinates a name. So our name here, the letters we're going to use here are going to be r, theta, and z. And z is not going to change. So z is going to be the same coordinate as we have in Cartesian coordinates. But for r and theta, how do we determine r and theta? Well, this point that I drew is not on the xy plane. So all you have to do to get r and theta is you just drop it to the xy plane. So we just take this guy and drop it straight down, and it will hit some point on the xy plane. And there we have a notion of r and theta, right? Here's r, and theta, again, is the angle made with a positive x-axis. So now, of course, you can, another way of interpreting theta, rather than just kind of moving it to the xy axis, you can kind of take a sort of the line that goes directly to the z-axis and sort of measure this angle of this sort of rectangle with the xz plane in the positive direction. So you can kind of take this angle here. Same angle. So that's all, there is really no difference. I mean, there's no extra complexity with cylindrical coordinates than just adding the C variable to the polar coordinates, sort of dropping things down to the plane. But let's write down the equation nonetheless for both cases. So if we have R, theta, and Z, we can easily write down the change of coordinates. And these, I believe, will be, someone asked at the beginning of class today about the exam and writing formula sheets. So I don't want you guys spending your time studying, writing down a bunch of formulas, unless that's helpful for you, but I don't generally have a formula sheet and don't allow formula sheets on the exam, but I do have a formula sheet that will come with the exam. So I will include a sheet of formulas with the exam. It will not be a surprise to you because I will give you a practice exam on Thursday. I'll put something on Canvas, a written practice exam. There's an online practice exam that all of you should do because you get extra credit for it. That will appear also on Thursday. You do not get extra credit for the written practice exam, too much grading. However, that's the one you really should work on because that's the one that is going to be more like the exam that will actually be happening. Anyway, there will be a formula sheet on the practice exam identical to one on the actual exam. So you'll see what formulas you're expected to remember versus those that I'll just, you can reference on this sheet. But these formulas, again, they're taking directly from the formulas for polar coordinates. We're going to take R cosine theta here, R sine theta here, and Z again is not changed. So it's the same as the Cartesian variable. And similarly, we have these formulas to translate from the Cartesian to the cylindrical. Sorry, I think I wrote the formula incorrectly. Yeah, I did. This should be tangent, not arctan. Sorry, guys, this should be tangent. You could put arctan on the other side. My bad. Okay. So what kinds of problems should you expect to see with cylindrical coordinates? Well, let's do an example. So here's a problem. So find the equation for the hyperboloid. So one thing I'll do, as I said, I don't expect you to remember the names of quadrics. I don't expect you to remember, I'm not going to give you a question that says, here's a quadric, what's its name? Identify the type of quadric. I won't do that. However, I may, on exams, use the language. Okay, I may say, find the equation for this hyperboloid and give you, well, let me write it out, give you this in cylindrical coordinates. So I may do something like this because this is just using language for me. But it doesn't require you to know that this is I'm telling you this is the hyperboloid. Okay, so let's say we give you such a problem. How do we solve it? Well, for a problem like this, so for me personally, what I like to do is I like to draw a picture and get a geometric understanding of what's going on and so on and so forth. I think that's a really healthy thing to be able to do. However, it's not a necessary thing to do to solve a problem like this. For a problem like this, one thing you can do is you can look directly at the equations and say, okay, how do I convert? Do I see in this, one thing you could do is you could literally just take X, Y, and Z, and then put their respective equations into this. And then you have a formula with the cylindrical coordinates, and then you can simplify that formula best you can. In this case, I see X squared plus Y squared, and I immediately think that's equal to R squared. Okay. So I immediately just say, okay, well, since r is equal to the square root of x squared plus y squared, we have r squared is equal to the sum of the squares, and I can just put it in. So r squared minus c squared equals 1. And remember, z is also a cylindrical coordinate, so this is an equation in cylindrical coordinates. And that's it. It helps, I will say, just also, now that we're back to, in-person exams and everything, when you're writing up exams, it helps to be very clear. So boxing off an answer is not a bad idea. You can draw, your grader's attention to the actual answer you intend versus maybe something you wrote somewhere else. So try to be clear with that. So this is an equation. And again, one thing I want to, so this is not a difficult problem. You just look at the equations and you go ahead and put them in the other coordinate system. However, you should observe what was said at the beginning. What is the main advantage of these alternative coordinate systems is they will reduce often the number of variables you have to consider. So here we had an equation with 3 variables and we've reduced it to 2 variables. That's a very helpful. Just lowering the number of variables in some kind of model is an extremely helpful thing to do computationally. It can drastically reduce the amount of time that some program or whatever you're working with, some model takes to actually work. And theoretically, you can often get solutions where you couldn't before. Okay. So that is cylindrical. And again, it's just a jump up, a slight jump up from polar, just add z, polar plus z. Questions? Okay. All right, so now we get to our favorite, our best friend, spherical coordinates. Spherical coordinates. Again, these have the advantage of really using spherical symmetry. So if you think of what kind of symmetry you're using for the different coordinate systems, I think for the Cartesian coordinate system, there's one symmetry that is very, very, very much present, which is translational symmetry. You can easily translate a shape in the Cartesian coordinate system. If you have an equation for something, you just take x minus, whatever, y minus whatever to translate that whole thing over. Translational symmetry works well with Cartesian. Rotational symmetry works really well with cylindrical in the sense that rotation about the z-axis. For spherical coordinate system, here you want to kind of exploit rotational symmetry sort of in both directions, sort of imagine a shape that is very much spherical. Oftentimes a sphere itself or a ball. So, but how do we get this? Okay, so let's take a point. And I'm not sure I remember the book. I'm trying to remember if I do the same way the book does it or slightly differently. The ordering of variables that I have may not completely agree with the book, but let me give you what I have. So I think the book does something a little bit not the way I would like it, but okay. So here I have a point, and let me label my axes, x, y, and z. And I want to give 3 constants. I want to give rho, that's pronounced, I mean, this is rho, Greek letter rho, theta, and phi, or phi. I pronounce it phi. Sometimes I switch. Okay. So there's one thing that's completely familiar, and it's theta. Theta is the same angle that we had in our cylindrical coordinate system. Okay. But before I get there, let's see what rho is. Maybe I should, I'll just keep it. Rho is the distance to the origin. So it's this length. Now theta theta is going to be, pain. There we go. Actually, I kind of want to imagine this is a little bit out there. Theta is this angle again. That's if you take this, if you make a right triangle here, and you take the angle between this sort of this side here and the positive x/z plane, theta is this angle. So I'll write theta here. Alternatively, again, it's the same as the polar, our cylindrical coordinate system. What about phi? Phi is this azimuthal angle, which is this angle made with the positive z-axis. It's that angle. By which I mean the angle, you take the ray from the origin to your point, and it gives you that angle. This gives you these coordinates. All right, so how do we, so that's great. This is, you know, we can at least geometrically understand what they are, but how do we actually write down an equation that will give us these coordinates? Well, rho, well, actually, let's translate from sort of the easier cases to translate from the spherical setup to Cartesian. So let's go that way. So let's do x, y, and z. So if we look at z is sort of the easiest, right? Z is just this length here. And so I look and I see I've got this right triangle. And if I want this length, then I need to just take cosine of phi and multiply it by rho. So this is rho times cosine of phi. So on the other hand, if I want to get y and x, what do I need to do? Well, that's what I'm going to do there is I'm going to first take this and move it down and over a little bit so I have a little more room. I'm going to drop this point down to the xy plane. Okay. Let's make a rectangle. Looks like I dropped it a little too far. So let's make a rectangle here. So now what I need to do is I need to find this length. I need to, okay, so I'm going to make, this is actually a pretty poor drawing, I'm sorry. I'm going to try to move it over just slightly. Let's pretend like that's the dropping point. There we go, that's a little better. All right. So what I'm going to do here is I need to, I have this theta here. This is my theta. And I can then take a triangle here, starting here, going here, or triangle here. Okay. And probably need to go here. And basically I'm after these two lengths right here, this length and this length. So I have this right triangle. I have these two right triangles. And I almost have this length. What do I need to find, you know, this x value, for example? I need the length of the hypotenuse of this triangle. I have this angle, but I need the length of, oops, sorry, yeah, of this hypotenuse. Sorry. And the length of that hypotenuse is given by the length of this, which is actually just rho times sine of phi. That's the length of this guy, which is not the x coordinate, it's just the length of this hypotenuse. However, if you think of rho times sine of phi, what are we actually determining here? It's sort of an intermediary thing. rho times sine of phi, we can put as our polar coordinate r, right? If we drop this down and we want this length, that's our r in the polar coordinate system, that length. So once we have r though, since theta is the same as the polar coordinate, we know what the formula is for x and y. It's r times cosine theta or r times sine theta. And we get these two formulas, which you can, let me rely on the result for polar coordinates rather than drawing these triangles over and over again like I was. So these are the formulas, and these again will be included on the formula sheet. I won't expect you to, these are harder to remember, I would say, but I want to convince you that you could figure them out if you just kind of look at these geometric diagrams. Going the other way, again, we have a distance formula for rho. If we have x, y, and z, this is just the usual distance formula, x squared plus y squared plus z squared, all square rooted. Theta is the same, so we can just take, if you want, you can put the tangent, or we can take arctan of y over x. Rho, rho, we can use this formula, right? And just take arc cosine, arc cosine of z over, and then using the formula for rho, x squared plus y squared plus z squared. So these we get three different, we can go from one coordinate system to the other without too much trouble. The key thing with these coordinate systems though, and we didn't see anything novel in the cylindrical coordinate setup because it was just based on polar, but we did see something in polar. The key thing about that is what are the restrictions on the variable? It's something really, really important to remember as you're trying to solve problems. If you forget it, you often are integrating too much or you're doing too much. You need to keep those bounds in mind as you go. So here we do have some new bounds. So theta is the same old bound. Well, maybe we should start with rho. Rho is non-negative, of course, right? We have this is representing a length or distance to the origin. Theta is the same as what we had for polar and cylindrical. So we'll keep the bounds here, say. And again, you could make this not a strict inequality if you wanted. What about phi? Well, phi describes this angle here, right? It's the angle made with a positive z-axis. So what we can do is we could take this guy and we can move it, and we'll see that phi grows and grows. If we bring it over here, if I, let me duplicate it instead. If I bring this guy over here, this is this, what is phi here? Phi is this angle, right? If I take this guy and bring it down, phi is going to be this angle, right? But what I can't do is I can't sort of exceed, I can go all the way to sort of the negative z-axis. But once I get to the negative z-axis, this angle is going to be 180 degrees. If I keep on going, it's going to start tightening up again. It's going to start decreasing. So the maximal angle for phi is going to be pi. So these are the bounds for the spherical coordinates that we want to keep in mind. These bounds will come up, especially when we do when we do integration. Okay, so let's look at a problem of changing coordinate systems to spherical coordinates. So let's find okay, I'm going to do this one instead of this. Other one's too simple. So find the equation for So you want to be able to go both ways. I can give you an equation in Cartesian coordinates, translate it into cylindrical or vice versa, or spherical or whatever. Go from one coordinate system to the other. So let's say find the equation for phi equaling pi over 4 in Cartesian coordinates. So why, by the way, why is it called Cartesian coordinates? Hands? Who knows? Yes? Descartes, good. Descartes. Sort of the granddaddy of analytic geometry, among other things. I don't know if he was actually a granddaddy though. Anyway. All right. So we want to find this, and we want to put this into Cartesian coordinates, right? So again, for me, what I do is I think, oh, what is that? It's saying that phi is going to be pi over 4, which is 45 degrees. So it's all points such that this angle is going to be 45 degrees. And then I think about it and I try to understand what that looks like and so on. If you don't want to do that, you don't have to do it, but you do have to be careful. Why? Well, what we can do is we can observe this formula here. I look for something. If I see this equation phi equaling pi over 4, I'm going to look for some change of coordinates that has as few of the other variables as possible. Here I've got a theta. Theta is not determined here, which means theta can be anything. Anything between 0 and pi over 2, or sorry, 0 and 2 pi. So these equations, for me, don't appeal to me right away because they involve theta. But here I've got an equation that just involves phi by itself, right? Because rho, I look up, I can convert rho easily. So I using this equation, change of coordinates, we have z is equal to rho times cosine of phi. Cosine of pi over 4 is square root of 2 over 2. So this is square root of 2 over 2 times rho, which equals square root of 2 over 2 times the square root of x squared plus y squared plus z squared. That's an equation. That's true, but it's kind of funky. I don't love it. So let me square both sides to make it a much more familiar equation. If I square it, square root of 2 over 2, of course, is 1/2. So I get 1/2 times x squared plus y squared plus z squared, multiply by 2, and I get, maybe subtract the z squared. Well, maybe I'll just do it in 2 steps. So 2z squared equals x squared plus y squared plus z squared. I can write this or 0 is equal to x squared plus y squared minus z squared. And if I am 80% of you, 75% of you, I don't know. I don't want to quantify you guys. You guys are all individuals. I circle this or put a box around it or rectangle or whatever. And I say I'm done, right? Am I done? Are you, if you were doing this problem, would you stop here? Would you feel good? Or satisfied? I don't know about good. Huh? It's not coordinates? It looks like coordinates to me. So this is the set, this is an equation. What do I want? I want to find an equation for this equation, but using the other coordinate system, the Cartesian coordinate system. This is an equation in Cartesian coordinates. So this, the set of points satisfying this equation will give me some set of points in three-dimensional space in the Cartesian coordinate system. And I want to say that that set is describing precisely the set of points in the spherical coordinate system that satisfies that equation. Yes? From here to here? From here to here. I squared both sides. Or second to the third, here to here. I subtracted this from both sides. So this plus turned to minus. Sorry, my arithmetic is sound in this case. I'll tell you that much. I'm not always, I make plenty of mistakes, but this time my arithmetic is sound. But maybe I failed to observe something. I did something. It was like my son when he was 1 year old. I just wrecked something. Didn't mind at all. Force of destruction. What did I wreck? This is what these are the subtle points. I want to do this problem because it gives you one of the subtle points. I'm forgetting something. I'm forgetting about bounds. I'm forgetting about the fact that when I went from this equation to this equation, I squared. The set of points satisfying this equation have a property. They have a bound, right? The z in particular has to be non-negative. Has to be non-negative. If I take a square root of a positive, I get it. I mean, if I take a square root in real numbers, I have to get a positive value. That's the definition of the square root function. So this gives me a positive value. Whereas here, once I squared, I just allowed negative z's. Now negative z's can satisfy this. The solution, if you look in the book, this is also a quadric. This equation is a quadric. It's sort of a degenerated quadric. It's a cone. Describes, this kind of thing. Let's see if I can. It's like a cone. This is a mathematical. Describes that. If you look, however, if you started the way I like to start, which I like to kind of see what I'm drawing, what I'm trying to describe, the equation phi equals pi over 4 is just telling me that this phi angle has to be pi over 4. So this is giving me this upper part of the cone, right? This lower part of the cone would have a phi equal to 3 pi over 4. And that gives me a negative here. So in fact, when I squared, I did indeed simplify my equation to look very good, but I added a whole another copy of a negative cone onto that shape. Okay. So of course, if there were a problem on an exam, you'll get like 8 out of 10 or something, for getting this solution. You'll still get a lot of partial credit. And I encourage people to try all of the solutions when you're doing work like this and show all your work. We will be generous with partial credit. Okay. The one other thing I wanted to, again, draw your attention to is this equation is simpler than this equation. 3 variables with squares versus 1 linear variable. We can use these coordinate systems to drastically simplify certain types of shapes when certain symmetry is present. Okay, guys, I didn't get a chance to talk about graph of functions. We'll start that on Thursday.